Systems of linear equations. What's a linear equation? An equation that forms a line when graphed. When I graph these equations on a graph, it forms a straight line. A system is more than one line on the same graph. And these systems of equations, what I'm looking for is a solution, an ordered pair that will make both equations true, or basically equal to each other. What is it? One ordered pair that would be a solution for both of these equations. That's what I'm looking for. So in a graph, I'm looking for where that ordered pair, or where those lines would intersect to form an ordered pair. That would be my solution. All right, so everybody got your notes set up? Okay. So in example 1, all right, let's see. I'm going to kind of take out some of this here because it's not really needed. Okay, on example 1, and this is what it's going to look like on your homework tonight, you're going to see a graph. And that graph, those lines intersect, and you can see that with the black dot. All right, so the point at which they intersect is the solution. What is the ordered pair that represents that point? What's the ordered pair? Whoa, whoa, whoa. X comes first. 1, -2. So I write 1, -2. That's my solution. So on numbers, on your homework tonight, numbers 10, 11, and 12, that's all you do. You look at the graph and you write the ordered pair. That's the solution. You box that in. That's your answer. All right, now on 7, 8, and 9, numbers 7, 8, and 9 on your homework tonight, it gives you this ordered pair, and it says, tell whether or not that ordered pair is a solution. So this is a way that you can check it. Let's say that you graph one of these and you think that you know the ordered pair that's the solution, but you want to just make sure. Okay, there's a way to tell whether or not that ordered pair is a solution. Here's how I do it. I take this ordered pair and I plug it back in to the original equations, both of them. I plug the ordered pair back into the original equations. So for the first equation, what value would I plug in for y? -2. What value would I plug in for x? 2 times 1 minus 4. For the second equation, what value do I plug in for y? -2 again, equals, but now I have -3 times 1 plus 1. I want you to simplify both sides of this equation. Do they check out? Do they both equal or not? All right, so 2 times 1 minus 4 is -2. So that one's good. And what's -3 times 1? -3 plus 1? -2 equals -2. So that one checks out too. So my answer is yes. And really all of this is part of the solution because you're just showing that both equations do work out. All right, so any questions about testing the solution? Like I said, in numbers 7, 8, and 9, this is what you're doing, is you're just testing the ordered pair to see if it's a solution. Good so far? All right. So now let's look at example 2. Example 2 is different. Before you look at the graph, don't even look at the graph yet. Look at these equations right here. What do you notice about the m value or the slope of both of those equations? They're both not just negative, but they're both the same exact value, -2. Do you see that? The slope here is -2 and the slope here is -2. So because of what I know about parallel lines have the same slope. Before I even graph, I know that those lines are parallel. Do you see the connection, guys? Do you see how I can tell just by looking at the equations? So on your homework tonight, when you're doing your homework, if you see that two equations have the same slope, you automatically know that they're parallel. And if they're parallel, will they ever intersect? No. So on parallel lines, if they have the same slope, here is your answer. No solution. no solution. That's why in the example it says no solution. Because they never cross. They never intersect. So equations with the same slope have no solution because they never intersect. Now, you still will graph it just to show that, just to give that extra evidence. But before you even graph it, you know there's no solution. You're not looking for an answer. Okay? Got it? Understand? All right, so that's no solution. But now let's look at example 3. Now there's a couple things I'm looking at first. Again, don't look at the graph yet. Look at these equations. What do you see that's different now, though, about these equations? Can I just tell what the slope and y-intercept are? They're not in function form. Go ahead and put these two equations in function form. Put them in function form. Okay, so same equations without the graph. What you're doing right now is you're taking these equations and writing them in function form. All right, I'm just kind of shifting off of that screen for a minute. All right, rewrite them in function form. Okay, so function form, y equals 2x plus 3. Did you get it? Function form on this one, what was it? Y equals 2x plus 3. Oh, well, that's kind of interesting. It's the same equation, right? So when you plot this on a graph, what's going to be true about your intersecting points? How many are you going to have? It's only one line. It's literally going to be the exact same line, right? It's the same equation. Infinite solutions. It's literally an infinite number of solutions. It's intersecting at every point. It is the same line. All right? It is the same line. So let's recap. If two equations have the same slope, what do we know about the solution? If they have the same exact slope? They're parallel and there's no solution. If they are the same equation, both of them, what do we know about their solutions? Infinite number of solutions. So the only other option is if they have a different slope. If they have a different slope, what do we know about their solutions? How many are there? How many intersecting points can a line have? A straight line have? If it's a straight line, how many intersecting points can they have?
Oh, no.
One. They only intersect at one point. They're straight lines and they only intersect once. Okay? So same slope parallel, they never intersect. No solution. Same exact line, infinite solutions. If they have a different slope, at some point they will cross, but only once because it's a straight line. Okay? Those are my three options. So this critical thinking exercise right here, all right, that's basically what it's talking about. If the graphs of two linear equations have different slopes, how many solutions will it have? And what did we just say? One. Why?
Because it only intersects once.
Give a verbal explanation. What would your verbal explanation be? Right? Okay, because different slopes, straight lines, linear equations, they will only intersect once. A graphical justification for that would just be for you to just show two lines intersecting. That would be fine. All right, but you just need to understand that. All right, different slopes, a straight line will only intersect once. All right, so now let's go back to this classwork. This is where we're going to spend a few minutes today. What I want you to do is, first of all, I just want you... is this one in slope-intercept form? Yes. Okay, so we're going to leave that one alone. Is this one in slope-intercept form?
No.
Go ahead and write that one in slope-intercept form. We need both equations in slope-intercept form before we graph them. I guess we could do one at a time, but let's just start here. All right, so x minus y equals -3 when I subtract x and then divide everything by -1. Did you do that? Okay, so what do you get? You get y equals x plus 3. All right, what about my second system? When I add 4x and then divide everything by 4, what do I get? Y equals
X plus 3.
x plus 3. Oh, snap. What's that going to be?
Infinite solutions.
Infinite solutions. Okay, so that one's not bad. Well, since that one's infinite solutions, let's go ahead and do the third one. Go ahead and write these two in function form, because that one's not going to be very fun to graph. It's just one line. I want to graph the ones that actually intersect.
Oh, I didn't know.
Oh, this one might be parallel. Let's see. Go ahead and write them in function form.
Yep, the parallel.
Are they?
Yeah, the y's and the negative x's.
Well, go ahead and rewrite them. Y equals...
Negative 3x minus 1.
No. You add 3x. Y equals 3x minus 1. And then on the second one, y equals negative 3x plus 4. Okay, so we're not going to graph this second one because we all understand that it's infinite solutions, right? So now I want you to go to your graph paper, and I want you to graph number 1 and number 3. How are we going to graph these? How are we going to graph these?
By your information.
Okay, do I need a table? Do I need an XY table?
Yes.
Do I need to substitute my zeros and find my intercepts?
Yes.
No, I don't even have to do that. What can I use?
M and B.
M and B. Plot your y-intercept first, and then use your slope to find the next point. All right? So let's see. So this is number 1 that I'm doing right now, the very first one. Okay, so you don't necessarily have to write this, but I am just so it's clear. Y equals 4x plus 2 and y equals x plus 2. All right, so graph both of those equations on this graph. All right, so what is the y-intercept on the first one? 2. It's not frozen. Okay, so 2, and what about, how would I use my slope? How do I know where my second point goes? What is it? Up 4 over 1, because it's 4 over 1. Rise over run. Line. What about my y-intercept for the second equation? Oh, that's 2 again, right? So my point's already there. How do I use my slope to find my second point?
There's a 1.
There's a 1 there. So 1 over 1, I go up 1 over 1. Do your lines look like that? What ordered pair do they intersect at?
2.
Nope.
No.
What is the ordered pair that they intersect at?
0, 2. Yeah.
Solution. 0, 2. So guys, plot your y-intercepts, use your slope, draw your lines. Where they intersect is your solution. The ordered pair is your solution. Okay, so now I'm graphing these two equations. Where do I start? What do I do first?
Go to your y.
Plot your y-intercept and then use your slope to find the next point. Go ahead and do that. Are y'all still working on that?
No, I finished.
Did they intersect?
Yep.
Did you write your solution?
Yep.
Alrighty, so here we go. Alright, so we plot our point at 4. And then where do we go from that point?
Down 3 over.
Down 3 over 1. And plot our point.
Oh, yes.
Down 3 over 1. Plot our point.
I went to the negative 1.
Ah.
That might be why.
Okay, now on the next one, we go negative 1. Plot our point. And then we go up 3 over 1. 1, 2, 3 over 1 here. Okay, so then we draw our line through here. So the exact point where they intersect is at what? 1, 2.
1, 2, 3.
1, 2. Over 1 up 2. All right, did you see that, guys? Who got 1, 2? Who got 1, 2? Good, Samantha. Good. All right.
I got -16.
Example 4 in our books actually requires a graphing calculator. So instead of kind of doing half of it and not doing the rest of it, let's look at number 6 on your homework, and I'll kind of get you started on it. You have 3 problems on your homework tonight where you have to write your own system of equations. You've got to write your own. You have to use the information to write your own system of equations, 2 equations. Here's what I want you to kind of break it up into. You have your big picture equation, okay? That's just to simplify. This plus this equals my total. And then you have your equation that is, basically the calculations to get to the total. Calculations. All right, so this is kind of the nitty-gritty. Well, how do I get to my totals? Am I multiplying some numbers together? Am I dividing some numbers by each other? Hint here, most of the time it's multiplication. All right, so let's look at number 6. On a wall of a shoe store, on one wall of a shoe store is used to display court shoes and running shoes. There's enough room on the wall for 120 styles of shoes. Based on past sales, the store manager wants to display twice as many running shoes as court shoes. Write and solve a linear system. Ding, ding, ding. 2 equations, linear system, to find the number of each type of shoe to display. So, my big picture, all right? What is the total number of shoes that belong on the wall? 120. That's my big picture. And what makes up those 120 shoes? What makes it up? What is he putting on the wall? What types of shoes? Running shoes and court shoes. So we use X and Y to represent those variables. We have to decide, though, and this is like number 22 as well, which variable represents which. We write it in the order that it appears in the problem. So X is running shoes, and you need to notate this, and Y is court shoes. Okay? So here, big picture. Running shoes plus court shoes equals 120. But I don't know which is which. I don't know how many. That really is my ultimate question. Well, I've got to come over here to my calculations. What do I know about the relationship between running shoes and court shoes? The problem gives me a hint. Store manager wants how many as many running shoes? Twice as many running shoes as court shoes. So, court shoes equals think about it. What if there were 10 court shoes? How many running shoes would there be? 20. So if 10 was plugged in for Y, I would multiply that, double it, and that would be my running shoes. Y equals 2X. Y equals 2X. So now here's where, so that's it, okay? And this really is what I'm most concerned about, is that you can actually write the system. Now here's the problem with actually graphing this to find my solution. That's going to be my y-intercept, 120. So I need a graphing calculator. All right, so we're just going to end it there. All right, as long as you can write the system, that's all I'm concerned about. And that's the same with number 22. I want the system of equations. You do not have to solve it because we don't have graphing calculators. Same with number 23. I want the system of equations. You do not have to solve it. All right? Thumbs up? Good? Okay, so hopefully that helps you figure out the systems of equations. This example 4 by far is the most difficult one, but I'm confident that you guys will be able to do it. All right, if you understand that, that's everything you need to know for 8.8.